Hi everyone. Today we are going to look at a problem called job shop scheduling. A job shop scheduling is that there is a set of distinct machines that processes some jobs. Jobs are a series of tasks which require the use of particular machines for a known duration, which must be completed in a specific order. Job shop scheduling is to schedule the jobs in the machines to minimize the total time necessary to process all these jobs. Now we will look at a particular use case to define the problem. A company has received an order for three types of wallpapers. Paper 1 has a blue background with yellow patterns. Paper 2 has green background and blue and yellow patterns. And paper 3 has a yellow background with blue and green patterns. Every paper type is produced as a continuous roll of paper that passes through several machines. For paper 1, first the blue background and then the yellow pattern is printed. For paper 2, first the green background is printed and then the blue followed by yellow patterns are printed. Paper 3 starts with the yellow background followed by the blue and then the green patterns. We depict this process by the following diagram. Here we see that there are three machines printing green, blue and yellow, and what is the sequence of each of the jobs through these machines that needs to be performed. We have the following duration in minutes for each of the machine to process the task for each of the papers. Now the problem statement is that knowing every machine can process one wallpaper at a time and the paper cannot be processed by several machines simultaneously, how should the paper printing be scheduled on the machines in order to finish the order as early as possible? Here we see one dependency of each of the tasks on the other tasks. So what we have mentioned over here is that the tasks to be performed by each machine on each paper is numbered 1 to 8. And the dependency of each task on its previous task is expressed with an arc. For example, the task 6, which is the task for paper 1 to be processed in the yellow machine, is dependent on the task 1 where the paper 1 has to be processed in the blue machine first. Similarly, paper 2 has to be performed in the green machine first and then in blue machine followed by the yellow machine. For task 3, it has to be operated on the yellow machine first, then it should be processed on the blue machine followed by the green machine.
Now we will see an application where we see the output and try to visualize the usability of this particular use case. We will first select the input file and we are able to see what is the defined input data. So as we have seen that there is a set of tasks and then there is a set of prerequisite tasks for each of them and the duration of the tasks in each machines. Now we will solve this problem. So what will happen is that on click of this button, it will invoke the optimization program that is written in Pymo, and then it will bring out the output from that program. So what we see over here is that the output brings about how the job is scheduled in the machines and then how the machines are allocated to each of the jobs. In this, we see that the maximum amount of time taken or the optimized time taken is 97 units.
We formulate the mathematical formulation where we define I to be the set of all the tasks. We are interested to know the start of each task. So we define a variable x which is of type binary to state the start of each task. We have a disjunction condition which we will see later, and that condition is represented by a variable y. The total time to finish all the work is represented by the parameter z, and the duration of each task is represented by that parameter d. Now we have a set of conjunctive and disjunctive constraints. So conjunctive constraints are that the condition where the precedence between operations for a single paper type is defined as the set of arcs. What we mean is that if the paper 1 is performed in blue machine, then the start of paper 1 in yellow machine should be, the start time should be more than the start time of blue machine of paper 1 plus the duration which it takes for paper 1 to process in blue machine. So if we represent machine 1 and paper 1, so we say that the start time of machine 1 in paper 1 plus duration of that task in machine 1 should be less than or equals to the start time of the paper 1 in machine 3. For paper 2, the start time of paper 2 processing in green machine plus the duration it takes should be less than or equal to the start time of paper 2 being processed in the blue machine, and the start time of paper 2 in yellow machine should be greater than or equal to the start time of processing paper 2 in blue machine plus the duration in the same machine. For paper 3, the start time of paper 3 processing in blue machine should be greater than or equal to the start time of paper 3 processing in yellow machine plus its duration. And likewise, for paper 3, the start time of paper 3 in green machine should be greater than or equal to the processing time of paper 3 in blue machine plus the start time of paper 3 in blue machine. So we can generalize this formulation as the start time of a job in machine J should be greater than or equal to the start time of task I in that machine plus its duration. The disjunctive constraints, whereas, is that a machine can only execute a single operation at a time. The condition is that either paper 1 is to be printed in machine 1 or paper 2 would be printed before paper 1 in machine 1. This is expressed by the following, where the start time of paper 1 in machine 1 plus its duration should be less than or equals to the start time of paper 2 in machine 1. If paper 1 is to start in machine 1 before paper 2, or if paper 2 is to start before paper 1 in machine 1, then the start time of paper 2 in machine 1 plus its duration should be less than or equals to the start time of paper 1 in machine 1. We can express this mutually exclusive constraints in the following way, where we can say that the start time plus a big M multiplied by 1 minus y1, where y is the disjunctive constraint which represents whether paper 1 is operating first in machine 1 then paper 2. Y would be 1 if paper 1 is operating in machine 1 first followed by paper 2, and y would be 0 if paper 2 is operating first in machine 1 followed by paper 1. To see the logic, if paper 1 comes before paper 2 on machine 1, then the y value will be 1 and we obtain the constraint as the start time of paper 1 in machine 1 plus its duration should be less than or equals to the start time of paper 2 in machine 1, and the start time of paper 2 in machine 1 plus its duration should be less than or equals to start time of paper 1 on machine 1 plus a big number. The first constraint requires that the processing of paper 2 on machine 1 takes place after the printing of paper 1 is terminated. Whereas the value start 1 and start 2 may take, the second constraint is automatically fulfilled due to the large value of M. On the contrary, if paper 2 is to be processed before paper 1 on machine 1, then Y has the value of 0 and we obtain the constraints as follows. This time the first constraint is automatically fulfilled and the second guarantees that the processing time of wallpaper 2 is terminated before the start of paper 1. We can generalize this formula in this following way, where the start of a task plus its duration should be less than or equals to the start of another task plus a big M value, given that the process I starts before the process J. The disjunctive variable Y is a binary variable. We define the data. We have set of 8 tasks, and then we have the duration for each task. So we define the tasks and the duration parameter. Then we have the set of arcs where we have the task 6 to be preceded by task 1, task 4 to be preceding task 2, and then task 2 will be preceding task 7. Similarly, task 8 will be preceding the task 3, and task 3 would be preceding task 5. We define the set of disjunctions where we say that the paper 1, 2, and 3 of task 1, 2, 3 would be performed in blue machine. So the disjunction is that 1, 2, and 3 would be performed in machine 1 or same machine. 4 and 5 would be performed in machine 2, and 6 and 7 and 8 would be performed in machine 3. We define the big M parameter as 400. The constraints are that the completion time for all the tasks should be less than the finish time. The finish time, as we have defined, is Z, which should be greater than all the start time of all the tasks plus duration of all the tasks. The second constraint is that the constraint of precedence condition for a single paper type at the set of arcs. So the task of operation on a single paper should have a start time which should be greater than or equal to the start time of the precedent operation plus its duration. So what do we mean by that is that the start time of, as an example, of task 6 should be greater than the start time of task 1 plus the duration which task 1 takes. The third constraint is that a machine can only execute a single operation at a time, and we have already seen this equation for for disjunction. The objective is to minimize the total cycle time, which is Z.
In the next video, we will see how to implement this problem in Pyomo.
We first create the data. So we save this file as a .dat file. We define the set of tasks. We define the parameter of duration. We define the set of arcs indexed by the set of tasks. We define the set of disjunctions. We define the big M value with a parameter M and assign it a large value. Now we create a file and save it as a Python implementation file. We first import the environment. The set of disjunctions, the parameter of big M, we define the variable of start and finish. We define the variable for disjunction. We just go back to variable and parameter declarations And just revise that the variable of disjunction condition is represented by y, where disjunction is that whether job 1 is performed on machine 1 first and then job 2, then y is 1, or job 2 is performed on machine 1 and then job 1, then y is 0. Hence the disjunction variable, and it is of type binary. Now we define the objective function. So objective function is to minimize the finish variable. Now we define the first constraint, where the constraint is that the finish time for the entire process should be greater than the start time of all the tasks plus the duration of each task. The second constraint is that of the conjunction constraint. To revise the conjunction constraint, it states that the start time of the next cycle, the start time of the next task for each paper should be greater than or equal to the start time of its preceding task plus the duration it takes to complete the preceding task. Now we define the constraint for disjunction. There are two constraints for disjunction. One is that either machine 1 is operating paper 1 first and followed by paper 2, or machine 1 is operating paper 2 first and then paper 1. So there are two disjunctive conditions. Second disjunction is defined likewise. Now we pass this model into the solver. We pass the name of the data file that we created to the instance. We will iterate through the set of tasks, and then we print the start times for each task, and then we print the finish time to know what is the total finish time the solver is suggesting. So we are looking two things to print. One is what is the start time of each task the solver is suggesting, and then what is the total cycle time to minimize the total cycle time as the solver suggests. So the solver has suggested what is the tasks to perform and what is the total time to finish the task. If we want to visualize this, this is how it looks. As we see, it suggests that job 1 will start after 42 minutes. Job 4 will be the first task to start. So it shows that we have the job 4, which is of printing the paper 3 in yellow machine. So we see that it states that job 4 to start. That means job 4, which is that the printing of paper 2 in green machine to start. So that's what it shows here. And then we are suggested to start the paper 3 in yellow. So now what it suggests is that job 4 and job 8 will be the first task to start. If we see, so job 4 was that paper 2 to print in green machine and paper 3 to print in yellow machine. So that's what the scheduler has suggested, followed by the paper 2 in blue machine, which is the task 4. So we see that job 4 will be the first task, followed by paper 2 in blue machine, which is task 2. So the scheduler suggests that the job 2 will start after 10 minutes. So job 2 was paper 2 in blue machine, which is to start after the paper 2 is finished in green machine, which has duration of 10 minutes. And then paper 2 in yellow machine. So paper 2 in yellow machine is task 7. So it says that job 7 will start after 53 minutes when paper 2 is printed green and blue. So paper 10 2 is printed green and then paper 2 is printed in blue. So it takes 30 minutes. So that's when it asks us to start the paper 2 in yellow after the green and blue. And hence we see that the total duration taken is 97 minutes. So this concludes our formulation of job shop scheduling.